All right, for this next set of four, we're going to check these out on DESMOS. Starting off right here with number 15. So we want the limit of this function as x approaches 5 from the left. So I already have these graphed for us. Again, we're talking about from the left. So we're looking at this green function. I'll move the dashed line out of the way for a bit. We've got this green function here, which definitely has a jump in it. So we want to make sure we're looking at the correct side. And in that case, we want to find out as x goes to 5, not 4.9, 5, there we go. What happens to this graph as we approach that dashed line from the left? And so that's talking about following along right here. Get closer and closer and closer to that dashed line. The y value there is -1. Probably can't see that from my scale. Note that we got 0 here, -1, -2. So problem with DESMOS, definitely make sure you're checking your scale. Also note you could just kind of drag your mouse cursor along there. You see all these y values are -1. So there we have it, -1. Jumping over to 16, now in 16 we're looking for a two-sided limit. Notice there's no plus or minus there, so I do care about jumps. I do want to make sure the left and the right match up. Let's see if they do. So I have my function graphed in purple here, and the dashed red line again, that's at x equals 1. That's where I want to check and see what the limit is. So note, if I kind of move that line out of the way there, the left and the right definitely meet. So we know that a limit's going to exist. The question is, what is it? A nice thing about DESMOS is if the function is defined there, you can actually click that intersection point. Notice in this case, the function is not defined there, so the intersection turns into an open circle. But I can scroll a little bit to the right, and I see a 0.499, and I can scroll just a little bit to the left and see a 0.50302, wigs out a little bit. So you don't need to build a table for these problems. DESMOS is pretty good at telling you right where that limit's at. So in this case, it's at 0.5 or 1/2 for all you fraction lovers out there. Let's jump down to 17. So for 17, I'm once again looking at a two-sided limit because there's no plus or minus in that upper right-hand corner there for the -2. So I want this thing to have both a left and a right side that meet at the same value. Let's see if they do. So my piecewise function is now in blue. We can see that dashed red line there is already set up at -2. And if I follow this function on the left, I've got that nice constant. If I follow this function along on the right, we note that those do not meet. So the left and the right limits are not equal here. They didn't ask us what the left and the right are, so I don't even care what their values are. All I care about is that they are not equal. So 17 is an example of a limit that does not exist. Important to note that if I were asking for this limit at any other x value, oh, I have my highlighter tool still on. At any other x value, the limit would exist over here. The limit would exist if I was over here. It is only at this one particular x value where the jump is, that's where the limit doesn't exist. Unfortunately, that's the limit they asked me for, so that's why we can't finish this problem. It just doesn't exist. All right, let's do a right example because we haven't done any of those in a while. We have another piecewise defined function. And again, this is one of those where we want to make sure we look at that graph. Note that that -3, well, that's where the break is. So we wouldn't be shocked if this limit didn't exist. Let's check it out. Now that is a beautiful piecewise function. I can scroll that dashed line off just a bit. We see that both the left and the right sides of that function do meet. They meet at a nice point there. It's a bit of a jagged edge, but that's okay. They meet at a point. So we know that that limit's going to exist. Again, if it's defined there, we can actually put our finger right on that intersection, and we get -3, 0. So these two functions are going to meet. The y value will be 0. Again, if it was undefined there, you could scroll a little bit to the right, a little bit to the left. For some reason, I can't scroll. There we go. Scrolling a little bit to the right, And you can see those values getting close to 0, and you can start scrolling from the left and see those values get close to 0. So that one is going to have a limit, and it's 0. So just because it's piecewise doesn't mean the limit doesn't exist. Some piecewise functions do meet in the middle. Let's go ahead and look at some trig examples, everybody's favorite. So looking at 21 here, this is a two-sided limit. As x goes to pi over 4, I want to know the limit of sine of x. Now, maybe you got a unit circle handy, but sine of x is defined at pi over 4. So that's just root 2 over 2. But hey, let's say you didn't have a unit circle handy and you actually wanted to check that because you love trig. There we go. Note that from the left side, sine approaches a value. From the right side, sine approaches a value. To find out what that value is, again, you could put a mouse cursor right there on the intersection point, or just use your finger if you're using a touch screen. And we wind up with 0.707, which is root 2 over 2 approximated. Let's look at one where we couldn't just look it up on a unit circle. For number 22 here, I want to look as x approaches pi over 4, but only from the right. Now, I have no clue what the function 1 over tangent of x minus 1 is, but DESMOS does. It's that pretty purple guy right there. So note that I only care about the right-hand side. So we're talking about this branch here, which goes off to positive infinity. The two-sided limit does not exist because the left-hand side goes to negative infinity. But since they only asked for the right-hand limit, that does exist. The right-hand limit is infinity. Let's take a look at another weird one. Take a look at number 23 down here. Again, asking for a two-sided limit because there's no little plus or minus there. So I want to look at both the left and the right-hand side to see what's what with this function. Now this is a secant function, and secant has asymptotes, so we know that there are some values that aren't very pretty here. But when we jump over to the DESMOS graph, that is one of the x values where things match up nicely. Note on the left-hand side we approach a value, on the right-hand side we approach a value, and they are the same value. In order to find out what that value is, if it's defined, of course, we can just touch it, and it is defined. You could also scroll a little bit to the left and a little bit to the right if that value was not defined and see what we approach. So we're going to approach negative 1.667. And one last trig example. This is another two-sided limit. So I want to look at both the left and the right-hand side to see what happens as x approaches 0 for this nasty sine x minus 1 over x function. Yeah. So here in green, we've got our function. I'm going to zoom out just a bit there. Again, I've got my x equals 0 line graphed, and if we were just looking for a one-sided limit, say we were going to the left, for example, that would exist. On the left, it's negative infinity. Unfortunately, they asked us for a two-sided limit. And because both sides of this function are going different directions, this is another limit which does not exist. So hopefully you've seen enough examples at this point. Limits that do exist, limits that don't exist, limits that are a nice number, an ugly number, maybe they're infinity. Hopefully you're feeling pretty warm and fuzzy using a graph to evaluate limits. That's this whole section, graphs and tables. In the next section, we're going to look at some algebraic ways to determine if the limit exists, and this is going to take us way back to like chapter 1, a little bit of factoring, a little bit of rationalizing, and all the goodness that Algebra 2 had to offer. So stay tuned, it's going to be great.